Hello chemists, this is Miss Placino and you are watching Screencast 10.2 on solubility. In today's lesson we're going to talk about factors that affect the solubility of a solute, and we're also going to talk a little bit about determining solubility of ionic compounds and using solubility curves. So this lesson is going to be really heavily dependent on your reference table. Make sure that you have it, otherwise you're putting yourself at a pretty big disadvantage. Alright, let's get started. We're going to start off by talking about ionic compound solubility. And this is something that we talked about when we were looking at double replacement reactions and trying to figure out which of the products, if either of them in a double replacement reaction, was going to be the precipitate. So hopefully you remember using this table, or now that you're seeing it again, you remember using this table. I want to quickly review how to use it just to make sure we're all on the same page. We've got these four columns. The one to the far left is talking about ions that form soluble compounds. And we talked a little bit about what soluble and insoluble means in the previous lesson. Hopefully you remember that soluble means able to dissolve in the solvent. And in this case, the solvent is always going to be water. In the column where it says exceptions, I want you to write insoluble. So ions that form soluble compounds, the exception to those rules tend to be very insoluble. These are the precipitates that would form in a double replacement reaction. We'll do some examples in just a minute. If you head over to the next column, it says ions that form insoluble compounds. So these are the ions that, when they're in a compound, generally end up, the compound generally ends up being insoluble. It will not dissolve in water. Things like carbonates, chromates, phosphates, so on and so forth, tend to be water insoluble. The exceptions we're going to label as slightly soluble. And I know that that is a very relative term. When you take AP chemistry, or if you take AP chemistry, you'll start talking about something called KSP, solubility product, and you're going to start putting numbers to these really vague topics or vocab words of soluble, insoluble, slightly soluble. You'll be able to get more exact definitions, but this is what we're going to work with at the Regents chemistry level. So for example, carbonates tend to be insoluble. However, if they're combined with a group 1 ion, so something like lithium, sodium, potassium, etc., or ammonium, NH4+, we'll get a compound that is slightly soluble. In other words, a relatively speaking small amount of that solid would dissolve in water. Let's try this out. Let's do a couple of practice problems. All right, I'm here in your workbook looking at practice problems, and practice problem 1 says determine if the following compounds are soluble, insoluble, or slightly soluble, and feel free to use the abbreviations SI and SS. And for the sake of practice, I'm just going to look at A through D. So we start off with calcium chloride, CaCl2, and unfortunately I got to scroll up so I can get to this. So I'll just write it up here, CaCl2. When calcium chloride dissolves in water, if it dissolves in water, I'm going to make calcium ions, and I'm going to make chloride ions. As for the sake of completeness, we'll get that equation balanced. So I usually start by looking at the anion, just because if you look at the table, almost everything, with the exception of the group 1 ions and ammonium, are anions. So what I want to do is find chloride on the table. And sure enough, here it is. Chloride, Cl-. So it's always soluble, compounds containing chloride, unless the cation is silver, lead, or dimercury. We've got calcium. Calcium is not silver, lead, or Hg2, so it is safe to say that this is going to be a soluble compound. So I'm just going to put an S. I can do the same thing for NH42S. Ammonium sulfide. Let's get this out of the way. NH4(2S). If it is able to dissolve, it's going to make 2 ammonium ions and a sulfide ion. I'll start with my anion again. I look for the sulfide ion, S2-, and I find it over here. It is generally going to be present in insoluble compounds. We've got some exceptions though. Sulfides are soluble, or slightly soluble I should say, when they're combined with a group 1 ion. No, it's not a group 1 ion. Or ammonium. Oh, that is ammonium. So ammonium sulfide is going to be slightly soluble. In other words, relatively speaking, small quantities of ammonium sulfide will dissolve in water. go ahead and try out lithium sulfate and potassium hydroxide on your own. Using the table, hopefully you're able to figure out that lithium sulfate is soluble. Sulfates are always soluble, group 1 ions are always soluble. Chances are this is a highly water-soluble compound. KOH, potassium hydroxide. Hydroxides are generally insoluble unless they're combined with group 1 metals or ammonium. Potassium is a group 1 metal, therefore that compound should be slightly soluble in water. As always, do the extra practice problems and make sure you're understanding this concept. When a compound dissolves in water, it can either exist as a saturated, an unsaturated, or a supersaturated solution. So I want to just kind of address what those terms mean. Unsaturated is when you take a relatively speaking small amount of the substance, your solute, and you dissolve it in solvent. So basically, unsaturated is telling us that the solvent is able to hold more solute. It's not full. I could continue to add more and more solute, and it's still going to be able to dissolve. There we go. The solid is going to dissolve when added to the solvent. If you keep on adding solute, and you do it slowly and carefully, eventually get to a point where you hit the solute's saturation. This is when the solvent cannot hold any more solute. This is actually going to exist at equilibrium, and this is a topic that's come up a couple times now since we started talking about chemistry. If we think about something like a saturated solution of sodium chloride, that means that we cannot dissolve any more sodium chloride into the water. When we say it exists at equilibrium, we've got two opposing processes occurring at the same rate. And this picture is trying to show you what's going on. The rate at which the sodium and chloride ions are able to be dissolved would be equal to the rate at which the sodium and chloride ions kind of come together to reform the crystal lattice. So this is the point where nothing else is dissolving into solution, and you have kind of this reversible physical change between dissolving and we call it recrystallizing. Did not leave myself much room for that. So dissolving and recrystallization, dissolving and reforming the solid, whatever you'd like to think of it as. Occasionally you can get something to supersaturate. This is a very, very delicate state. In a supersaturated solution, the solvent is holding more solute than it should be able to. So basically, it's hit its saturation point and you're continuing to add solute, and somehow it's able to dissolve. Usually we attain a supersaturated solution by taking something at like room temperature, adding tons and tons of solute so that you can actually see the solute like piling up on the bottom of the beaker or the Erlenmeyer flask, and then heating it. As we heat a liquid, usually solids are going to become more soluble in it. So you get everything to dissolve, and if you let it cool off really slowly, for some ionic solids, you're able to supersaturate the solution. But this is usually a very delicate, artificially induced state. If you disturb this supersaturated solution, either by sometimes just like shaking it will do the trick, adding a little bit more solute to the solution, you cause all that excess solute to crash out of the solution. And what we mean when we say crash is to rapidly recrystallize. So the rate of recrystallization is greater than the rate of dissolving. And since this is something that you really don't see all the time, I want to show you a video of it. We're going to show you a supersaturated solution of sodium acetate. If you look at the table F in your reference table, you'll see that acetates are always soluble, group 1 ions are always soluble, so sodium acetate should be very soluble in water. So let's check this out. All right, so in the Erlenmeyer flask, we have a supersaturated solution of sodium acetate trihydrate. We're going to take a little bit more of that solid, really small amount, just a couple of crystals, and we're going to add that to our supersaturated solution. When we add it, massive amounts of the solute are going to start to crash. It looks like it's turning into a solid, but that's not what's happening here. All the excess sodium acetate that shouldn't have been able to dissolve because we were already at the saturation point is coming out of solution. You can see everything just rapidly falling out of solution. As this happens, the solution gets really warm. Since it takes energy to dissolve all that extra solute, it's endothermic, and the process of all the excess solute crashing out of solution will be exothermic. It's a really cool physical change. We'll make sure that we show you that one in class. All right, so there are a couple of factors that can affect solubility, and we're going to focus just on two of them. With solids, think about trying to dissolve sugar in iced coffee versus hot coffee. Higher temperatures tend to increase the solubility of a solid. Pressure changes are going to have virtually no effect of dissolving a solid into a liquid. This really isn't going to matter. If we look at gases, for example, trying to cram carbon dioxide into champagne or soda, low temperatures increase solubility. If you start to increase the temperature, you're going to have the gas molecules moving around faster. And if the particles are moving faster, it's going to be harder to force them into solution. Gases are affected by pressure. So if you have a high pressure situation, you're able to increase the solubility. You can kind of think about yourself as like pushing and cramming more gas into that champagne bottle. It's not uncommon for champagne to be bottled under like 6 to 8 atmospheres of pressure. So you can get all that carbon dioxide dissolved. So when you pop the cork, you're going to get a nice big dramatic effect. The last thing I'd like to talk about are solubility curves. So this is just a really simple solubility curve. Only one substance is shown on it. So we have the relationship between temperature and the grams of solute, in this case potassium nitrate, dissolved per 100 grams of water. And potassium nitrate as a solid at room temperature, so just like what we talked about, this curve hopefully makes sense. We see that as temperature increases, so does solubility. We can dissolve more and more potassium nitrate into that same 100 grams of water. Let's say at 80 degrees Celsius, you got 50 grams of potassium nitrate dissolved. What is the state of that solution? Saturated, unsaturated, supersaturated? Well, hopefully, since you see it's below the curve, you can conclude that this is an unsaturated solution. You can keep dissolving more and more of your potassium nitrate into the water before it reaches its saturation limit. I know it's kind of tough to tell because we don't have a whole lot of tick marks, but right here is where we're going to reach saturation. Uh-oh, my dog. Sorry about that. Okay, as I was saying, it's a little bit tough to tell here because we don't have a whole lot of hash marks to help us out. But if we wanted to saturate this 100 grams of water with potassium nitrate at 80 degrees Celsius, we've got to reach the line. And that looks like, we'll call it about 170-ish grams or so. So if we can get to the curve exactly, that means the solution is saturated. So I'm going to write unsaturated down here. Saturated, oops, oh no. On the curve, and let's say that somehow you are able to dissolve 300 grams of potassium nitrate in 100 grams of water at 80 degrees Celsius. That's when you're going to hit supersaturation. But being above the curve doesn't always mean that the solution is supersaturated. You really would have to look at it on a case-by-case basis. If you check and you want to look to see if the solute is visible. If there is no solute visible, that means you've got a supersaturated solution. If you do see that the solute is visible and it's like sitting at the bottom of the beaker or the flask or whatever vessel you have the solution is, that just means that it is saturated and the excess solute has not dissolved. And the second one is generally far more common than getting a supersaturated solution. You might know from experience that if you take like sugar and you keep adding it to iced coffee, eventually you're going to get to the point where no more sugar can dissolve. It doesn't become a supersaturated situation. The excess sugar just starts piling up at the bottom of the coffee cup. That is much more common than getting something to become supersaturated or getting a solution to become supersaturated. So I want to use that reference table to help answer a couple questions. So let's look at the practice problems. All right, so this is right out of your reference table. It's table G, and as you can see, there's a whole lot more going on in this set of solubility curves than in the simple example I showed you in the PowerPoint. It's still the same idea. We've got temperature on the x-axis, we've got grams of solute per 100 grams of water on the y-axis, but instead of just having one solubility curve, we've got a bunch of them. So make sure that you are looking at the right curve. It's really easy to get confused in like this middle section of the graph where there's a whole lot of overlap. So just heads up, be careful about that. Let's try a couple practice problems. Let's look at questions like 1, 2, and let's also do number 5. We'll jump around a little bit. So question 1, how much KNO3 is needed to saturate 100 grams of water at 60 degrees Celsius? So first thing I do is see if I could find the KNO3. Sure enough, here it is, potassium nitrate. I want to know how much mass, basically, of potassium nitrate needed to saturate 100 grams of water. I know that saturation is on the line. So I'll get to my 60 degrees Celsius. I'm going to trace it up until I hit the line for potassium nitrate and trace it over. And it looks like about 105 grams. You might look at that and see 104, maybe your neighbor sees 106. A lot of times these will show up on the Regents as multiple choice questions, and they don't give you like 104, 105, and 106 grams as choices. It's like 105, 110, 100. There's a lot of room for interpretation. They just try to get you on really nitpicky things. Question number 2, at what temperature will a solution containing 60 grams of ammonium chloride become saturated? Same idea, find your ammonium chloride. There it is. I want to know what temperature a solution containing 100 grams of ammonium chloride becomes saturated. I'm going to go out on a limb and assume we're working with 100 grams of water at this point in time. I got to rewrite that question. So I'm going to find 60 grams. Trace across until I hit the line. Oh, there it is. I'm going to trace down until I hit the x-axis. And I see, I don't know, maybe 68 degrees Celsius or so. Again, same thing. You're not going to try to split hairs between 67 and 68. If you know it's somewhere between 65 and 70 degrees Celsius, you're in good shape. All right, question number 5. How many grams of NH3 ammonia are needed to saturate 50 grams of water at 60 degrees Celsius? Now you're probably getting sick of hearing me say it. Find your solute, ammonia, NH3. Oh, this is kind of weird. The curve is going down as temperature increases, solubility decreases. What should that tell you? This means that ammonia is a gas, and sure enough, at room temperature, ammonia is absolutely a gas. We want to know how many grams of ammonia are needed to saturate 50 grams of water at 60 degrees Celsius. So I go to 60, I trace up, I get to ammonia's curve, trace across, I see 22 grams of ammonia that will saturate 100 grams of water. Don't put it on autopilot and not read carefully. If I have half the amount of solvent, I'm going to need half the amount of solute. So if I get 22 grams per 100 grams H2O, if I cut my water in half, it is safe to assume that I'm going to cut the amount of ammonia that can dissolve in half as well. So in this case, I get only 11 grams needed to saturate that solution. Okay, I would definitely, I know I say it every time, go through, work with the practice problems, make sure that you are comfortable with these concepts. This lesson is really, really Regency. These type of questions come up all the time, and it's really all about, can you use those tables? Remember, New York State doesn't particularly care if you know chemistry. That is an added bonus, but they want to make sure you can read. So let's wrap stuff up. 60-second summary today. You have a beaker containing a solution of calcium chloride. The mixture is clear with no precipitate at the bottom. How can you determine the state of the solution? Explain your answer. Yeah, this is kind of a tricky one, but I bet if you kind of stop and think about it for a little while, you'll be able to figure it out. All right, I hope this lesson was helpful. Thanks for tuning in.